Okay, let's go ahead and get started. Um, so we sent out an announcement yesterday with an action plan. Uh, the good news is that we've managed to piece together. We now have 3 people to help me finish building out this course as we go, as well as catch up on the grading. Um, because of various regulations, we had to wait until we made the hiring decisions to be able to get them involved. So that happened over the weekend, and now we're ready to go. Uh, so things will be looking up, and starting this week. On the flip side, however, I'm going to need to cancel the Monday night sessions. It's just too late and too much for me. So we will have every Tuesday from here on out, but not the Monday night sessions. I am available by appointment. So if you do need something, let me know, and I'm hoping we'll be able to find times earlier in the day rather than late at night. That's really what was getting me. So, earlier during the day or early evening or weekends work well, but not that late at night. If there isn't a time where you and I can meet, then I do have a couple of other people that I can put you in touch with now that might be able to help you as well. But we'll handle that by email. So let me know if you need an appointment, and we'll make one. As I said, you'll start to see more materials appear now as we've gone out and recruited enough help. So let's just take a quick look at the website. You'll see there's a new folder for this week, and right now it's got the first lab in it. The second lab is ready to go, and I'm going to post it just after one last modification that needs to be made to update the problem set. But it's basically ready to go, and it'll be posted, and you'll have a couple more this week as well as a short assignment. And the assignment, just so you know, will be based on, if you go into the lab, you'll see at the end there are suggested exercises. The assignment will be similar to the suggested exercises, so you know what you'll be seeing. But as I said, we got people in place over the weekend, so we're going to start getting this built out in the next day or so. If you have any more questions on moving forward, please do let me know, and I'll do my best to answer them. Okay, so tonight it was requested that we do a brief review. A couple different students requested a brief review of the basics of confidence intervals and hypothesis testing from a classical standpoint. I know that when Amit did his presentation, it was on permutation tests, and the concepts are similar. But some of you have expressed concern over the distant past that your intro stats class was in, so you asked for a brief review. So that's the goal for tonight. We'll talk a little bit about the basic confidence interval approach. Let me go back to the presentation here. There we go. So we'll talk a little bit about the confidence interval approach. And then we'll talk about the hypothesis test approach. We'll talk about why hypothesis testing can be a little bit dangerous, and why perhaps we want to return to a confidence interval approach after all. It's not to say we'll completely do away with hypothesis testing, but they've come to dominate, and perhaps we should scale that back. So let's go ahead and jump into confidence intervals. The process is fairly simple, and again, this is in any introductory statistics textbook. And if you're sitting there saying, "But I don't have an introductory statistics textbook," it is also covered in chapter 7 for confidence intervals and 8 for hypothesis testing in our textbook. Now, there's a lot more detail in there, perhaps, than you would get in an intro course, but it's all in there. Okay, so the 5 steps. First, we start with a point estimate. And then we go on and calculate our standard error. We determine our confidence level. How confident do we want to be in our answer? We use those things to determine the margin of error, and then we calculate an interval. So let's take a look at these step by step. A point estimate. You guys do these all the time. For instance, for a sample mean, you'd add them all up, divide by how many there are. That's a standard mean. That's a point estimate for a lot of different probability distributions. If you think about the Poisson distribution, the best estimate of the parameter lambda for a Poisson distribution is to take a sample and calculate its mean. And we're going to see how to do that when we get to Chapter 6 here in a couple of weeks. There are two different methods that are commonly employed. Maximum likelihood is the most commonly used method. And there's an older method called the method of moments. So we'll get to those. But for now, we'll just assume that we have a formula, like in this case, for the sample mean. That's our point estimate. So if somebody says, what do you think the average, I don't know, height of students is, you'd go out and take a sample of a bunch of students and calculate the average height. That's the point estimate. That's the easy part. The next thing we need to do is do the standard error. And so what we do is we calculate the variance of our point estimate. And then what we really want, though, of course, is the standard deviation. So you can see here for a sample mean, we can calculate the variance. You learned all of this back in the probability unit. The variance of the sum of xi's over n, well, we can pull the 1 over n outside of the variance formula. And remember, when you pull a constant out, you square it. And then the variance of the sum becomes the sum of the variances. We have n of them. So we have 1 over n squared times n times the variance of x, which gives us just the variance of x divided by n. And the variance of x there is just the variance of an individual observation. And then, of course, we want the square root of that. So that gives us a formula that, if you took introstats, should be very familiar to you here. S, which is the sample standard deviation, divided by the square root of the sample size. So that's an example of how we would derive the standard error for a sample estimate, in this case the sample mean. The other piece that we need is the confidence level, and this is just how confident do we want to be in the answer that we give. So we're going to give an interval estimate of what we think the true value is for a parameter. Do you want to be 90% confident, 99% confident? How confident do you want to be? The more confident you want to be, the bigger your interval becomes, because you have to sort of capture more possible answers. And so there's a trade-off there, right? As you increase your confidence level, you decrease the precision of your answer. And so commonly accepted values in business, 90% is pretty common. That doesn't mean it's the only one that's used, but that's, to me, sort of the standard percentage to use for business. In medicine, 99% or even 99.5% is pretty common. And then if you're not sure what to do, sort of in science in general, 95% is pretty common. So a lot of examples will use a 5% significance level or a 95% confidence level just by default. So if you're not really sure what to do, that's a good place to go. Obviously, in medicine, where lives are at stake, we tend to want higher confidence. Just remember that comes with a trade-off of either having a less precise answer or having to counter that, you have to increase your sample size. So when you get into things like clinical trials for cancer drugs, you don't want to have too big of a sample size, right? So there are trade-offs to determining what level of confidence you want to use. Sometimes there's even legislation dictating what you have to use. So once we've determined the formula for the standard error and we've got our confidence level chosen, we need to calculate our margin of error. We're going to build a confidence interval around our point estimate using a margin of error. And so the margin of error is going to be the product of two different numbers, and we'll see the formula in just a minute. But the first thing we need to do is calculate what's called the critical number. It's the number of standard errors that we allow in each direction, and that's based on our confidence level. So for a mean, if we're estimating a single mean, we use the t-distribution, and we need to know, for the t-distribution, we need to know what's our level of confidence. So if it's 95%, that means we're going to put 5% of the probability in each tail. So you can see here I'm calculating t for 0.025, that's 2.5% in each tail. And then if I have a sample size of 40, then my degrees of freedom are 39. And this is, again, all covered in Chapter 7 of the book. The t-distribution is very similar to the normal distribution. It's just a little bit more spread out. And it approaches the normal distribution as your sample size gets bigger and bigger. So with a sample size of 40 and a confidence level of 95%, our critical number would be 2.023. Now you'll notice there's a negative sign there. I could have also done t of 0.975, 39, and then I would have gotten positive 2.023. It turns out it doesn't matter, and you'll see why in just a minute. But I got these from R. You can use the calculation that I show there to get the quantile from R. The reason it doesn't matter now is because when we do our margin of error and we calculate our interval, we're going to go in both directions. So if you use a negative critical number, you'll just cancel that out when you go in both directions anyway. So we usually just write down the number. We don't bother with the negative sign. So the margin of error is just how many standard errors away are we allowed to go, which is the critical number, times the size of the actual standard error. So for a sample mean, that would be S divided by the square root of n. And so when we calculate our confidence interval, it's just the point estimate plus or minus the margin of error. I see my plus or minus disappeared here. But it's the point estimate, so the sample mean, plus or minus the margin of error, which is the critical number times the standard error. So for our example, suppose we had a sample mean of 6.82, a sample standard deviation of 1.28, and our sample size was 40. We would get a confidence interval from 6.41 to 7.23. And so we would interpret that as we're 95% confident that the true mean is within that interval. And it's important to keep in mind, we are 95% confident that the true mean is in that interval. It's not that there's a 95% chance. Either it's in there or it's not. What we're really saying here is that if we went out and did this 100 times, we would expect that we would get the true mean in the interval 95 times out of 100. All right, so we're 95% confident that we've captured the true mean somewhere in that interval. And it could be anywhere in that interval. There's not a probability distribution on that interval. It just, 95% confident that the true mean is somewhere between 6.41 and 7.23. So that's the confidence interval approach. That should be familiar to you from introductory statistics. And that really, it's a pretty powerful thing. You get a fair bit of information from that, right? We've got a sense of how precise our answer is. It ranges over a spread of 0.82, and then context of the problem would dictate whether that's good or bad. And so this is a pretty useful thing. However, starting in roughly, let's say the 1920s, an alternative approach was formulated by a bunch of guys, Fisher, Neyman, and Pearson, and some of their contemporaries, and they formulated this approach of hypothesis testing. And so we use a confidence interval to estimate a parameter from scratch, but we use hypothesis testing if we think we know something that's going on and we want to test whether that's true. So I've listed 7 steps here. It's not that you need to be too formal about having steps 1 through 7, but this is just to outline the basic process. And there are a couple of things to keep in mind when you're doing hypothesis testing. You'll notice that collect data is step 5. It's not step 1 or 2. It will often in practice be step 1 or 2, but it's important that you do the things above that item here before you look at the data. You always want to specify the test and set it up before you examine the data. Otherwise, you run the risk of setting up a test to give you the result that you're hoping for. So you always want to specify the test first and then collect and examine the data. Sometimes you're given the data so you don't have the option of collecting it later, but you just have to make sure don't look at it first. Run the test on the data once you've specified the test. So let's take a look at the step-by-step here. The very first thing is to formulate the question that you're interested in. So an example for us tonight will be, does a particular drug reduce systolic blood pressure? There are a couple of reasons that I'm choosing this as my example question that I guess will be clear when we get to the end. So that's the very first thing we need to do, is we need to ask what's the question we're interested in. Once we've done that, we can specify our hypotheses. And so the way we set this up, as Amit went over, is that we specify a null hypothesis, which is to say that there's no actual effect, that any variation is just due to chance. And so in this case, the null hypothesis would be that the drug has no effect. And then the alternative hypothesis is that there is a real true effect. And we need to turn those into quantitative expressions. So what we'll say is mu, which will be the mean decrease in blood pressure due to the drug, equals 0 for the null hypothesis, and that the decrease is greater than 0 for our alternative hypothesis. In other words, that it has an effect. Now, we could have set this up as mu equals 0 and mu less than 0. It just depends on the way you calculate your difference. If you do before minus after, you would expect to get a positive value if the blood pressure medication lowers the blood pressure. If you did after minus before, you would expect to get a negative value. So you just have to make sure you set them up to match what you're expecting when you do your actual calculations.
Hey, Mike, can we just say mu is different than 0 so we can have both sides instead of greater or less? Can we just say mu is different than 0?
You could do that. Yep, you could do that. But in this case, we have a very specific alternative that we're interested in showing. We want to show that the drug reduces blood pressure. So we're not interested in a drug where the effect is in the opposite direction. There certainly are times where we'll say, what effect will this have? And it might be positive or negative, we don't know. In which case, you're right, we would specify just mu not equal to 0 as the alternative. An example of that might be if you do a marketing campaign and you just want to know, did it have any effect? There are marketing campaigns that actually have a negative effect on your sales. So yeah, there absolutely are times where we would do it as a two-sided test. Tonight I'm going to just do a one-sided test because we want to show this drug reduces blood pressure. So if our sample shows that it increases it, then that's not of any interest to us. Right? We're not going to bother with the drug any further. Okay? Yep, good question. Okay, so we specify the test, or rather we specify the hypotheses. The next is to choose the type of test that we're going to do. And again, we want to do this before you look at the data. And the reason for that is if you look at the data, you might decide that one test will give you a better result than another. And when I say choose the test or specify the test, keep in mind we've got a lot of different tests available to us. So permutation tests, for instance, are one type of test for a difference in means. So another type would be a two-sample t-test, which is covered in introductory statistics. So there are different tests you can use for the same problem. So tonight I'm focusing just on a classical single-sample t-test. So we would say we're going to run a one-sided t-test. It's one-sided because the alternative hypothesis is one-sided. And I'm going to choose a 5% level of significance, and I'll talk about what that means in a little bit. But again, 5% is kind of the standard, although in this case, since we're using a blood pressure medication, we might have wanted to go with 1%. But I chose 5%. Once you've specified the test that you're going to run, you need to calculate, okay, if what needs to happen for me to reject my null hypothesis. We call that the rejection region. And so what we're going to do for a one-sample t-test is we're going to see, under the null hypothesis, how many standard errors away from the mean do I end up? And if I end up too far away, we're going to reject the null hypothesis. We're going to say it's just not likely to be true. And so the critical value that I calculate here is going to tell me where my rejection region is. So when I run my test and I calculate the standard error for my sample, if it's greater than 1.687, I'm going to reject my null hypothesis and say that I have evidence supporting the alternative. So this is based on the specification of the test. We often will do this in terms of probability or p-values as well. But for now, I'm going to stick with the classical test here. And only now I've specified exactly what outcome will tell me the result of my test. Now I can take a look at data. So I would go ahead and collect the data, or perhaps if I've already got it, I would go ahead and do the calculations. And so let's pretend I do that and I get these results. I get a sample mean of 24.2 millimeters of mercury. So that's saying that the systolic blood pressure on average for our sample was lowered 24 millimeters of mercury with a sample standard deviation of about 40 millimeters, so 39.8 millimeters. And my sample size, in this case, I'm going to go with 38. And that was based on just the fact that I had used that in my example up above. And we'll talk a little bit more about how to choose a sample size later. So this is my numerical data and the summary statistics from the data, and I'm now in a position to go ahead and run the test. So I plug the statistical values that I just calculated into my test statistic, and this formula is dictated by the test that I'm running. So you'll notice that I'm calculating what was my sample mean and what was my null hypothesis mean, which was 0. And I'm dividing that by my standard error to tell me how many standard errors away am I from what I expected if there's no real effect. And so 24.2 was my sample mean, minus 0, which is the null hypothesis mean, right, that there's no effect, divided by the standard error, which is the same formula that we saw for the confidence intervals above. So 39.8 divided by the square root of 38. And when I do that, I get a test statistic of 3.748. And I'm now in a position to draw a conclusion. Remember we said if we got a test statistic greater than 1.687, we would reject the null hypothesis. 3.748 is greater than 1.687. Therefore, we're going to choose to reject the null hypothesis, and we'll make the claim that we have evidence to suggest that the medication reduces systolic blood pressure. Remember, in statistics, we never say we have proof. What we say is we have some evidence to suggest this. In this case, it's reasonably strong evidence. And in fact, had we chosen a 1% level of significance, we still would have had enough evidence here. But remember, we don't want to do that too much. We don't want to do the calculations and then ask ourselves what level of significance we should use. We always want to specify that ahead of time. There is a slightly different approach to the drawing of the conclusion. And the idea here is that you calculate the probability that you would get the result that you got or a more extreme result under the null hypothesis. So for the t-distribution, I would calculate what's the probability that I land above 3.748 for a t-distribution with degrees of freedom equal to 37, which is always one less than the sample size. And if I do that, I get a value of 0.0003. And I actually didn't do this integral. The t-distribution formula is pretty nasty, but you can get this in R very easily, just using the pt function. And so what this says is that there's a 0.03% chance that I would have gotten this extreme result or more extreme if there's no real effect by the drug. And since 0.0003 is less than our level of significance of 0.05, we would choose to reject the null hypothesis. So there's the test statistic approach. Let me go back to that here just for a second, where we reject if our test statistic is greater than our rejection value. And then there's the p-value approach, where we reject if the p-value is less than our significance level. They are mathematically equivalent. The p-value approach gives you a little bit more information, so that's good. Because you could reject at 1.8, or you could reject at 3.8, or you could reject at 9.8, because they're all bigger than the 1.687 that we were allowing. But if all you report is that you rejected, then the person reading your report doesn't know what that p-value was. So the p-value is generally preferred these days because it gives you a little bit more information. However, all that said, that's the basic process for hypothesis testing. All that said, there are some challenges. The first of which is just, it's statistics. We might get the wrong result. The second thing that can go wrong is that we can misinterpret the result. And the third thing that can go wrong is that there's no practical significance. So let's just talk a little bit about each of these three things. So results can be wrong. And in particular, we can be wrong in two different ways. So this table here sort of expresses that. One thing we might do is we might reject the null hypothesis even though it's true. Really unlikely events do occur from time to time, right? So if we have a 5% significance level, what we're saying is that we will reject the null hypothesis as long as that probability of occurring under the null hypothesis is less than 5%. But that would suggest that roughly 1 in 20 times we might be rejecting when we shouldn't. So that can happen. We call that a type 1 error, where we reject the null hypothesis even though it's true. the level of significance is what we use to control for the probability of a type 1 error. Right? So when we say level of significance 5%, what we're really saying is we're willing to allow a 5% chance of committing a type 1 error. All right? And so that's how we control for type 1 errors. Type 2 errors, then, are where we choose not to reject the null hypothesis even though we should have done so. And the way we typically control for type 2 error is by sample size. And so we're going to get more into that in the future. I'm not going to talk about that tonight, but we typically use what's called the power of the test to worry about type 2 errors. So we'll talk more about that. I'm guessing it'll either be next week or the week after, where we'll talk about the power of a test. But just keep in mind, we can draw the conclusion correctly according to the formulas, but it might still be wrong in reality. Right? We might correctly reject the null hypothesis according to our procedure, but we really shouldn't have, and that would be a type 1 error. So we want to keep in mind, we can be wrong about these things, even if we do everything right. The second challenge is that p-values are easily misinterpreted. Keep in mind, it's the probability of getting what we got for our sample test, or a more extreme result, if the null hypothesis is true. It's not a measure of the size of the effect. So you can get a really tiny p-value, and I would consider 0.0003 to be pretty small. And you can get that from either a really big effect, or you can get it from a really tiny effect, but with very little variation. And I'll show you what that looks like here in the next slide, where we talk about statistical versus practical significance. So you can imagine you're looking at 2 blood pressure medications, and if you build a confidence interval, you can see I've drawn confidence intervals for 2 different medications. In the first case, it's a very small effect. It's maybe somewhere between 4 and 8 is what the confidence interval says. But because 0 is not included in that confidence interval, we would say that it's a statistically significant effect. If we ran a hypothesis test, we would reject the null hypothesis. In the second drug, our confidence interval is huge. It's anywhere from about -2 up to maybe 70 or 75. However, 0 is included in that confidence interval, right? And so if we ran a hypothesis test, we would fail to reject the null hypothesis. We would say, we do not have evidence to reject the null hypothesis. There's no evidence that the drug has any real effect. But if I put it to you as the question, which drug would you choose? If you're looking at lowering your blood pressure, an effect of 4 to 8 millimeters of mercury, while not nothing, it's not huge, right? If your systolic blood pressure is about 200, lowering it to 192 isn't exactly great, right? I mean, that's just not a big enough difference. In the second case, it might not be statistically significant, but the chances are it'll have a much bigger effect. And so if you do a simple cost-benefit analysis of this, I'd be more inclined to go with the second drug rather than the first drug, just because there's the upside potential that's not there from the first drug. So statistical significance is not the end of the story. You want to keep in mind that there needs to be practical significance as well. And if the effect is just too small, even if it's there, if it's just too small, then it might not matter. You can always get an effect if you get a big enough sample size, so you want to keep that in mind too. You don't want to just keep increasing your sample size until you get a statistically significant result. You want to keep in mind practical significance. So these are some of the dangers of hypothesis testing. So just as a conclusion, I would caution you to be careful using hypothesis testing or significance testing. It is pervasive. Everybody uses it these days. It's all about p-values if you read reports. But confidence intervals give more information. They're easier to interpret, and it's easier to tell when you have the potential for practical significance rather than just statistical significance. So going forward, I would keep that in mind. There are times where we want to use hypothesis testing. I'm not saying it should go away altogether, but keep in mind confidence intervals can give more useful information, and I think should be used more often. You don't always need to run a test. So that's a brief overview of confidence intervals versus hypothesis testing. Again, if you're interested in more detail, an introductory statistics textbook would have it. And in fact, let me point you at one while I'm thinking about it. If you're interested in an introductory level book that's free, if you go to openintro.org, they have all sorts of resources here, and it's all free. But they have Open Intro Statistics, which is the second edition of their textbook. And you can actually download it as a PDF file. You can download it as a tablet-friendly PDF file. And then they have extra content here. And in fact, one of the things they have that might be nice if you don't have a computer handy, although then I ask you why you're able to look at this online, you can actually get the probability tables that we always use for doing our calculations. And in fact, one thing I'll show you here, you'll remember that with a sample size of 38, we said we had 37 degrees of freedom at a one-tail 5% significance level. You'll see here that the critical number is 1.69. I believe I was using 1.687. So you can always use probability tables to get those values. But this Open Intro site has a lot of good resources. It has good resources on R as well. So if you're interested in running some labs in R, check this out. Right there's a lot of good stuff here, and it's changing every day. It's changed a lot. It's changed a lot from even just about a year ago, to the point where I don't even know everything that's here anymore. But they have Data Camp, which is some interactive labs that you can do. So I would encourage you to check these out. It's not a bad resource. Shaker, okay, so that's actually a very tough and interesting question. We typically start moving into a design of experiments sort of environment for that. We're not actually going to cover that in this course, but there are various techniques for multiple group testing. You have to be careful because you can't just, for instance, you can't just use 5% for each group. So there are some dangers of how do you spread out the probability from that significance level. But typically we would take a design of experiments approach and look at multiple groups. And there are all sorts of different methods for doing that. In fact, I'm wondering if the Open Intro book gets into that. Let's actually take a look. And if not, I can point you at some other resources that you can look at. So no, it doesn't look like they do. I can point you at some other resources on multiple group testing. The concepts are actually very similar, but the formulas get a lot more complicated. Other questions? Okay. Actually, if there are no other questions, let me take a minute to point you at one potential resource. This is my favorite statistics textbook for what I would call an advanced undergraduate course. It doesn't cover everything we're doing, so we didn't choose to use it for this course because we wanted to get into the resampling methods. But let me just show you this. Modern Mathematical Statistics with Applications. So if you want to go ahead and snag a copy of this book, I believe it's a little bit pricey. It might be available through the Baruch library, but it's a pretty good textbook. And Shaker, to answer your question, it would get into the details of what you're looking for in analysis of variance here. And you get into multiple comparisons. So that's the sort of place where you would find answers to that kind of question. And I'd be happy to work with you through that separately if you're interested. Any other questions at this point?
Oh, Mike, you mentioned about the material that we should be using for this section. You mentioned Chapter 7 of what textbook?
Of the Mathematical Statistics textbook for the course.
So that is Chapter 7, right?
So right now we're in Chapter 3 on hypothesis testing in the labs that you guys are working through. So this was really meant just to give you an overview of the approaches. But if you're interested in the stuff that I covered tonight in more detail, confidence intervals for means, The stuff that I covered tonight is in section 7.1.2, confidence interval for a mean where the standard deviation is unknown. We almost never know the true standard deviation, so section 7.1.1 is almost a waste of time. But 7.1.2 talks about how to do the confidence interval for a mean, and in fact it shows you the R code for doing it as well. And then hypothesis testing is in chapter 8, and so you can find section 8.1.1, and 8.2 covers the types of errors. So if you're interested in more background reading on the two different approaches, those are the two chapters that really cover the classical approach that you learn in Intro Stats. But right now we're still in chapter 3 for the lab materials. And again, lab 1 was posted yesterday, lab 2 will be posted tomorrow. I'm hoping lab 3 will be up tomorrow, but it'll be up by Thursday, if not tomorrow. I've just got...
So these labs, it should be, so Mike, I'm just looking at the website. So this lab should be under hypothesis, whatever this week is, April 27th through May 3rd.
Yeah, so this is chapter 3. So the first lab is just an introductory lab. It actually reviews some of the same concepts we just covered. And then there are 3 suggested exercises here. And if you go back, I think I actually, let me see if I can get back to the course website. You'll see here that solutions are available as well. You'll know you're looking at the solution sheet because it's got orange instead of blue. And so we've got solutions to each of the questions for you here. And those are all chapter 3 based. And at the beginning, oops, let me go back to the lab. At the beginning of the lab, it tells you the reading for the lab. So sections 3.1 and 3.2 for this lab.
I'm actually trying to find this on the site that I have. Can you go back for a second and just point me like where you click?
Here?
Hypothesis testing, right? Yeah, lessons.
In the week, in the lessons.
Oh, so it's under lessons. Okay, got it.
Yep, and then once it's created, the assignments will be posted under assignments. And again, you guys have been wonderfully patient, but we finally were able to get a few people hired now, and we're starting to build this stuff out. So my role is more coordinating that. So you'll see stuff, and I'll send out announcements as stuff gets posted too, so that you know it's there.
All right, cool. Thank you very much.
Mike,
let's see. 2 people are talking at once, so I guess.
Hey, Mike, can you please go back to those 7 steps that you mentioned for the hypothesis test? I just want to write them down because I think they're very helpful.
Oh, in my presentation for the 7 steps.
Right.
Yeah. I'll tell you what. Let me edit mode on and click into lessons, and I'll just post the presentation for you.
Thank you.
Item. Let's see. I need to bear with me as I do this, folks. Let me end the slideshow and save it as a PDF file for you.
All right. Thank you very much. Great.
Mm-hmm. Oops. There we go. Let's see. Let me apologize while I navigate my folders here. Let me see where it went here. Okay, let's make sure that posted. But you can now get this slide deck so that you can look at it and use it. So there you go.
Great, thank you.
Yep, looks like it worked. Okay, let's see. So the solutions for the week 8 labs, I got them today, and I will post them tomorrow, Sonia. So yes, I actually just got those from one of the TAs today.
Mike, would there be any final project or before the end of the course?
We'll have a final exam that'll be it'll feel like a few small projects. It won't be massive theoretical questions. It'll just be practical questions. But we won't have a big project. Eventually we hope to have group projects incorporated into the course, and we'll make those available to you later, even after once they're built. So that'll probably be for the summer, but we'll make them available to you. Obviously, you won't have to do them for your grade.
Okay, so when is the last working day of the semester? Because I see that 25th of May is a holiday, so it should be 22nd. But in the syllabus actually, it was listed till 26th, I think.
Here we go. So spring is May 17th is the last day of classes. May 24th is the last day of the official final exam period. But if I pull up the syllabus here, give me just a second. I'm looking for the right version. Okay, so we will have a couple of extra days there if you need more time. And so I think we said like the 26th or something like that for the final, because grades aren't due until like the 28th or 29th. So officially May 20th through 24th is final exam week. I think I allow a few extra days if you need more time. Does that give you a good enough answer?
Yeah.
I mean, the expectation is that what we give you can be done by the 24th, but if you need a couple extra days, I'm happy to allow that. Okay. It just has to be in before grades are due so that I can submit a grade. And if it's not, we would give you an incomplete and ask you where it is and get it figured out. Any other questions? Okay, why don't we end there? I'm going to try, in the future, I'm going to try and make these sessions about 45 minutes rather than a full hour. That's partly for my own sake, but obviously if you have questions, we can keep going past that. So that'll allow an extra 15 minutes if you have questions. Let me know if you have questions. Send me an email. I'm going to have one of the TAs also checking the discussion forums to keep me in the loop. The idea is to do some of the things that I just can't get to, and we'll go from there. Okay, so
hey,
yep,
Mike?
Yep, go ahead.
Do you have like a rough calendar for the next coming weeks, the next couple of weeks that we have left?
I don't have an exact one. I know you said rough. I would estimate that this week we'll do Chapter 3. Next week, which is to say Star Wars week, right? May the 4th be with you. There you go. We'll cover Chapter 4 and start into Chapter 5. And then the third week, May 11th, we'll cover the rest of Chapter 5 and touch on Chapter 6, just the first two sections. And then the last week will be Bayesian, so Chapter 10. And we won't cover the whole chapters. That'll give you a good foundation for the data mining course, which is really what's next for this stuff. And then there's some other stuff that we missed just because of circumstances that you'll have access to once it's built out. So 3, 4, 5, 6, and 10 are the chapters we're going to be covering, and this week 3, next week 4, 5, the following week 5, 6, and the last week 10. And I'm looking forward to the Bayesian stuff because we have a couple of really neat applications from hockey analytics, and of course we'll be getting very close to the Stanley Cup Finals at that point. If you don't care about hockey, then you'll just have to pretend and watch our silly little demos. But I think you'll enjoy it. I think you'll see why it's such a powerful approach. And then there's talk at some point down the road of perhaps even offering a full Bayesian statistics course. I imagine Derek would be the first to sign up. So, okay.
Mike, I have one last question. Sorry.
Go ahead. No, that's fine. That's fine.
Yeah. Actually, while reading all this material on the hypothesis testing, the permutation testing, and other stuff, I was wondering, what kind of approach do you usually follow in the industry? As a data scientist, do we follow the permutation testing, which is pretty easy to interpret and understand?
Yes. I'll cut you off there, and I'll just say yes. The classical approaches have a lot of flaws. The primary reason that we are exposing you to them even in this class is so that you know them when you see them. But if you're doing it yourself, I think the resampling methods tend to be much better. They're easier to understand. They're easier to interpret. They tend to be more reliable, although not always. And there are fewer assumptions behind them, and that's always powerful. So, when you do a classical hypothesis test like what I showed tonight, you're assuming that the data are roughly normally distributed, and that's almost never the case. Well, I won't say almost never, but it's often not the case. And so, just permutation testing has fewer assumptions, so it tends to be a better approach.
Yeah. Okay. Thank you.
And when we get to the bootstrapping chapter, you'll see more variation on the different approaches. So permutation testing is for a difference of two means, right? But there are other resampling methods for other kinds of questions, and so you'll see a lot of those. And I would say go to those first if you're not sure what to do. The only time to use the classical approaches are if somebody that is in a position of authority over you tells you to, and even then maybe push back a little depending.
Thank you.
You're welcome. Any other questions? Okay. Again, email me if you have any questions, and we'll go from there. And otherwise, I guess I'll see you all next Tuesday, same time. And in the meantime, have a good week. Thanks, everyone.